Hello, Namaste. Thermal engineering. And this thermal engineering first topic, fundamentals and laws of thermodynamics. Previously, we discussed in the last lesson uh, what is thermodynamics, what is thermal engineering, what is system and classification of system, what is property, what is the state, path, process, quasi-static process, and different properties like pressure, volume, density, etc. We had discussed in the previous, and what are the types of properties also we completed. Now in this lesson, let us see the objectives of this lesson. On completion of this lesson, you would be able to know modes of energy transfer, define specific heat, internal energy, enthalpy, and also know about flow work and entropy. And some simple problems, solve problems on fundamentals of thermodynamics. Modes of energy transfer. First one is the modes of energy transfer. And for most of applications in the area of thermodynamics, mass is considered constant while analyzing the energy in transition. Mass is considered constant while analyzing the energy in transition. So heat and work are two most fundamental energy forms. Heat and work are the two most fundamental energy forms, and heat energy. And heat is defined as the energy crossing a system boundary because of temperature difference. Energy crossing a system boundary because of temperature difference between the system and surroundings. Once again, the heat is defined as energy crossing the system boundary because of temperature difference between the system and surroundings. So heat contained by system can only be identified and felt only when it crosses the boundary. Heat is a path function. Properties are all the properties generally are the most of the properties generally are the point functions, whereas the heat is a path function, and that is the amount of energy transferred when a system changes from state 1 to state 2 depends on the intermediate state through which the system passes. That means it depends on the path. Once again, the amount of heat energy transferred when a system changes from state 1 to state 2 depends on the intermediate state through which the system passes. That is, depends on the path of the system. That's why it is a path function. And hence heat is an inexact differential, whereas the property is a exact differential, as heat is not the property of the system, and also it is the path function. That's why it is inexact differential. And the heat transfer to or from a system undergoing a process from state 1 to state 2 can be written as heat transfer Q1 to Q, capital Q1 to 2. This can be written as like this, and integral of 1 to 2 dou Q. So this is the, because it is inexact differential, this can be written as in this way. And where Q1 to 2 represent the amount of heat transfer when the system changes from 1 to state 2. Right? So heat is expressed in joules, generally in joules or in kilojoules. The units for heat, energy or heat are the joule or kilojoule. And sign convention for heat transfer. Sign convention for heat transfer, So heat energy flowing into the system, that means from surroundings to into the system from the surroundings, is called to be positive. That means if the heat is flowing from outside to, that means surroundings to into the system, then it is positive. That means simply we can call it as heat supplied to the system. And heat energy flowing from the system to the surroundings is said to be negative. That means heat is rejected by the system. First one is the positive. If the heat is flowing to the system, into the system, is the heat supplied to the system, which is the positive. Whereas if the heat is flowing from system to the surroundings, it means heat is released from the system and entering into the surroundings, then it is negative. That means heat is rejected by the system to the surroundings. Right? This is the same convention for heat transfer. So suppose here you can see this is the system and this is the surrounding and this will be the boundary. And if you see heat energy is a Q1 is entering into the system, that's why it is the positive. That means heat is supplied into the system, because that's why it is the positive. Whereas in this here heat Q2, that means heat energy is leaving the system to the surroundings, to the from the system to the surroundings is negative. That means heat is called heat rejected by the system, whereas heat is supplied to the system. So this is the sign convention for heat transfer. And one work energy. Work energy. In thermodynamics, work may be defined as work is energy transferred. Work is energy transferred without transfer of mass. Without transfer of mass across the system boundary because of a property difference other than temperature. Work is energy transferred across the system boundary because of a property difference than other than temperature, whereas the heat is due to temperature difference, whereas heat is the property difference other than temperature. If there is a temperature difference, then it is heat. Whereas if it is the other than temperature difference, it is not the temperature, but it may be volume difference, or it may be pressure difference, or it may be any other property difference, then the work is to be transferred, work energy transferred across the system boundary. Right? So work is not a energy stored, work is not or a energy stored or processed by a system. It is not a property of the system and depends on the process, but it is not the property, and it is not stored or it is not processed, but it depends on process by which an energy transfer is taking place. It depends on the process by which energy transfer is taking place. Thus, the work is a function of path of the system followed during its change from state 1 to state 2. That's why it is an inexact difference. Number one is the work is the path function. Previously, as we told, heat is also path function, and it is depends on path only, as not it is not depending on the points or the states. And heat is the inexact differential, work is also inexact differential. So work for a system undergoing a process from state 1 to state 2 can be written as W, capital W, 1 to 2. This the indication for work transfer or work for a system, and integral of 1 to 2 dou W. This is the writing process for work transfer undergoing when the system undergoing a process from state 1 to state 2. Where W1 to 2 represent the amount of work done by the system or on the system, work done by the system or on the system when it changes from state 1 to state. So sign convention for work transfer. Sign convention for work transfer. The sign convention for work transfer is appropriate to that of the heat transfer if the work is done by the system on the surroundings. Work is done by the system on the surroundings, it is denoted by positive. Work is done by the system on the surroundings, it is the positive, whereas the work is done on the system by the surroundings, it is denoted by negative. Once again, work is done by the system on the surroundings is the positive, and work is done on the system by the surroundings, it is the negative. And work is expressed in joules, which is also equal to Newton meters, or kilojoules, also kilonewton meters. So this is a sign convention for work transfer. This is a sign convention for work transfer. And 1 Newton meter is equal to 1 joule. So here you can see this is a system boundary, system, and this is the boundary, dotted line, so it's nothing but the system boundary. And if you say this is entering into the system, that means work is entering into the system, that means work is done by the system into the, work is done on the system by the surroundings, it is the negative. Work here is work is done by the system as the piston is moving outward. Work is done by the system on the surrounding is the positive. So right, this is the sign convention for work transfer. So now comparison of heat and work transfer. Heat and work. Heat is transferred across because of temperature difference between the system and surroundings, and work is transferred because of property difference other than temperature. And heat and work are both transient phenomena, and systems never possess heat or work, but either or both crosses the system boundaries when a system undergoes a change of state. But heat and work are boundary phenomena. They are observed at the boundaries of the system and represent energy crossing the boundary. Both the heat and work are path functions and then inexact differentials. Now the specific heat. Specific heat. Specific heat may be defined as the quantity of heat required to raise the temperature of Specific heat may be defined as the quantity of heat required to raise the temperature of 1 kg of substance through 1 degree centigrade. Specific heat is a function of temperature, and for solids and liquids the value of specific heat varies with temperature. In case of gases, it depends on path of the process also. In case of for solids and liquids, it varies, that means specific heat varies with temperature, whereas in case of gases, it depends on path of the process also. Specific heat. If specific heat is supplied to 1 kg of gas keeping pressure constant through 1 degree temperature difference, then it is called specific heat at constant pressure. That means once again you can define this as the amount of heat or the quantity of heat required to raise a temperature of 1 degree for 1 kg of substance through 1 degree when the pressure remains constant is called specific heat at constant pressure. When heat is supplied to 1 kg of gas keeping the volume constant through 1 degree temperature difference, and it is called specific heat at constant volume CV. And specific heat at constant volume can be represented as CV, whereas the specific heat at constant pressure will be represented as CP. So what is specific heat and what is specific heat at constant pressure and what is specific heat at constant temperature? The specific heat at constant volume CV, that is mathematically CV is equal to dQ by dt, and if V is constant and CV is equal to du by dt, specific heat at constant pressure Cp is equal to dQ by dt. If pressure is constant, then dH by dt. And the specific heat Cp and Cv of a gas varies with temperature. However, for moderate temperature, they may be assumed constant. For air, the value Cp is equal to 1.005 kilojoule per kg Kelvin, whereas the specific heat at constant volume is equal to 0.715 kilojoule per kg Kelvin. So now the internal energy. Internal energy may be defined as the energy stored or possessed by the system. Energy stored or possessed by the system. The molecules of gas are in a state of motion, thus possessing kinetic energy. The total kinetic energy of molecules is called kinetic energy of the gas. And internal energy, molecules attract one another and therefore they have potential energy also, which is called internal potential energy. The sum of these energies, that is kinetic energy because of its motion of the molecules, and because of by the position, and the potential energy is called the total internal energy of the gas. Actual gas possesses both the types of internal energies. Actual gas possesses both the types of, that means kinetic energy as well as potential energy. In a perfect gas, however, there is no internal molecules attraction, hence its potential energy is zero. No, in case of perfect gas, there is no internal molecules attraction. That's why there is no potential energy. That means potential energy will be zero for perfect gases. The internal energy of the perfect gas, therefore, consists of only the kinetic energy of its molecules. The internal energy is a property and only depends on end states. The path of the process occurring between the same two states is immaterial. That means the internal energy is the property of the system, number one, and it is depends on the end states only, but not on the path of the process. That's why the path is not important in this internal energy. That's why it is the only the property. The internal energy is independent of pressure and volume, and only it's a function of temperature. But the two states, the total change in internal energy is given by the equation U2 minus U1 is equal to mCV T2 minus T1. That means, as it is the property, we are going to represent like this. This is the internal energy at state 1, state 2, and it is the internal energy at state 2. That means initial internal energy, this is the final internal energy, and this is the temperature, final temperature, and this is the initial temperature, and this is the mass, and this will be the specific heat at constant volume. So the internal energy per unit mass of gas is called specific internal energy. The internal energy per unit mass of gas is called specific internal energy, and internal energy is expressed in joules or kilojoules. Enthalpy. Enthalpy or total heat. Enthalpy or total heat is defined as the heat supplied to a system at a constant pressure. Heat supplied to a system at constant pressure and represented by capital H, or sometimes like internal energy. Enthalpy is a point function and depends on only temperature. The change of internal energy between two end states is given by H2 minus H1 is equal to mCp T2 minus T1. Enthalpy also defined as the sum of internal energy and the product of pressure and volume. So here for enthalpy, two definitions we can have. Heat supplied to a system at constant pressure is nothing but the enthalpy or total heat, or it is the sum of internal energy and the product of pressure and volume. So H is equal to U plus PV, and enthalpy H is expressed in joules or kilojoules. That means units for enthalpy are either joules or kilojoules, whatever it is. Enthalpy per kg is called specific enthalpy, which is represented by small h, which is represented by small h, and it is in joule per kg or kilojoule per kg. And flow work. Flow work. The work done in moving the fluid into or out of the system. The work done in moving the fluid into or out of the system is called flow work. Consider the fluid crossing the boundary at 1,1 in figure. Say here, this is the cross section 1,1, and if it is crossing the 1,1 and if it is having a dx thickness, so area of this is A. The approaching fluid must displace an equal amount of fluid inside the system in order to cross the boundary and enter the system. The energy required to achieve this is called flow work. Flow work is equal to force into displacement. Force into displacement. So force is equal to pressure into area of the boundary and into displacement is equal to dx. So A into dx is nothing but the volume. That is A into dx is equal to volume of fluid flow. So that's why P into V, flow work is equal to pressure into volume. So unit for flow work is also same as the work, that is joules or kilojoules. So where P is the pressure of the fluid either in Newton per meter square or kilonewton per meter square or kilopascals or pascals, whatever it is. So this is all about the flow work. Now the entropy. Entropy is an extensive property of system that will increase by addition of heat, decrease by removal of heat. It is an extensive property of the system that will increase either by addition of heat or decrease by removal of heat. Like internal energy, it depends on end states of the system and it does not depend on the process by which the system undergoes from state 1 to state. Means it is independent of process or path of the system, but only depends on the end states. The change of entropy during the process is expressed as ds is equal to dq by t, where dq is equal to amount of heat supplied or rejected. Amount of heat supplied or rejected. T is equal to absolute temperature at which the heat occurs. So entropy expressed in joule per kg or kilojoule per kg. So this is all about the theory part, and let us have a small problems on this lesson. In this lesson we have discussed about the energy transfers, that is work transfer and heat transfer, internal energy also we have discussed about, enthalpy also we completed, and also difference between work and heat, and also entropy we completed. Now let us have small or simple problems on this lesson. The pressure on the cylinder varies in the following manner, that is P is equal to C by V, where C is equal to constant, where P is equal to pressure and V is equal to volume. Find the work done if the initial pressure is 400 kilopascals and the volume changes from 0.02 meter cube to 0.08 meter cube. Here is the volume is changing and initial volume is this much. With this, P is equal to C by V. Find the work done. So now the solution for work is the P is equal to C by V, or PV is equal to C, that is equal to P1 V1 is equal to P2 V2. So initial pressure P1 is equal to 400 kilopascals or 400 Newton per meter square, whereas initial volume is equal to 0.02 meter cube, and final volume V2 is equal to 0.08 meter cube. Now let us find the work done. Work done 1 to 2 is equal to integral of 1 to 2 is by C by V, where P dV, and is equal to, if you see coming outside, that is integral of V1 to V2 1 by V dV. So if you integrate with this, C into log base E V1 to V2 and C into log base E V2 minus log base E V1, that is C into log base E V2 by V1, and finally C is equal to PV, and PV is equal to log base E V2 by V1. So with this formula, this is the work done formula. So with this, P is known for us and V is also known for us. Initial P, say let us say P1 or V1. P1 is known for us, V1 is also known for us, V2 also known for us, V1 is also known for us, V2 by V1. So finally we will get V2 by V1, and then V1 is log base E V2 by V1. If you substitute all the values, you will get your work, that is 11.09 kilojoules. 11.09 kilojoules is the right answer in this problem. So let us see once again this problem. So here is the pressure is equal to constant by volume. If you bring to this side, PV is equal to constant, that is P1 V1 is equal to P2 V2, and also if you substitute, if we are having as W1 to 2 is equal to integral of 1 to 2 into P dV. If you substitute it in place of P C by V, then you will get, so this formula, that is integral of 1 to 2 C by V. This C by V is nothing but the P dV, and the C is the constant that we can bring outside. So V1 to V2 1 by V, that will be give you 1 by V, or into dV is equal to, will give you log base E into V. That is, finally we will get C log base E V2 minus log base E V1, and C log base E V2 by V1, and then C is equal to either PV or P1 V1 or P2 V2 you can take. So here P1 V1 log by C V2 by V1. Finally, you got the formula for work done. And after this, these values P1 is known for us 400 newtons, sorry, kilonewtons per meter square, and V1 is also known for us, and V2 is also known for us. V1 is also known for us. That's why after substitution, you will get 11.09 kilojoules. Here, this is the formula. So, right. So, problem number 2. Problem number 2. 1 kg of air is heated. 1 kg of air is heated from 20 degrees centigrade to 105 degrees centigrade. Find the change in internal energy and change in enthalpy. As we are having the previous formulas as discussing about the internal energy as well as the enthalpy formulas. For internal energy, change in internal energy formula is MCV, that is U2 minus U1 is equal to MCV T2 minus T1. Similarly, for change in enthalpy is equal to H2 minus H1 is equal to MCP T2 minus T1. So here assume Cp is equal to 1.01 kilojoule per kg, kilojoule per kg Kelvin, and Cv is equal to 0.72 kilojoule per kg Kelvin. So the solution here is the given is mass of the 1 kg is given to you, and then initial temperature is 20 degrees Celsius, and that should be converted into Kelvin, 293 Kelvin by adding 273, 220, sorry, this is not the 200, this is 20 plus 273, 293 Kelvin. And final temperature T2 is equal to 105 degrees Celsius, that is plus 273, you will get 378 Kelvin. So Cp is also known for us 1.01 kilojoule per kg Kelvin. Cv is also known for us given in the data, that is 0.72 kilojoule per kg Kelvin. So as we are having from the discussion of internal energy and enthalpy, change in internal energy is equal to C U2 minus C1 is equal to M CV T2 minus T1, and we are having M 1 kg, Cv is also known for us, T2 is also known for us, T1 is also known for us. The substitution you will get change in internal energy, that is 1 into 0.72 into 378 minus 293, that is 61.2 kilojoules. So that is the change in internal energy. Similarly, a change in enthalpy formula H2 minus H1 is equal to MCP T2 minus T1. That is mass is known for us, Cp is also known for us, T2 is also known for us, T1 is also known for us. After substitution, you will get 1 into 1.01 into 378 minus 293, you will get 85.85 kilojoules. So with this, we got the answers for change in internal energy and change in enthalpy. Right, let us have the summary of this lesson. So in this lesson, we learnt about modes of energy transfer. There are two forms of modes are there. One is the work transfer and heat transfer modes are there. And also specific heat, we defined the differences between work as well as heat also we had discussed about. And specific heat is nothing but the amount of heat required to by 1 kg of gas for rising of 1 degree Celsius. Also internal energy we have discussed about, and enthalpy also we have discussed. And flow work we completed, entropy also we completed. And two simple problems also, worked out problems also we completed in this lesson. So let us have some small quiz. So let us have small quiz on this lesson. Which one of the following is an extensive property of thermodynamic system? Volume, pressure, temperature, density. Extensive property means it depends on the mass. So pressure is not so, temperature also not so. So volume will be the right answer in this. And which one of the following is not a property of the system? Pressure is the property, thermal conductivity is the property, composition is not the property, and also heat is not also a property. So this question itself is wrong. Which one of the following is an intensive property of the thermodynamic system? Volume, potential energy, temperature, and entropy. Temperature will be the intensive property. And quiz in this once again, among following, which one is a point function? Heat is the path function, work is also path function, whereas internal energy is depending on the states, that's why it is the point function. And units for specific internal energy, kilojoule per kg, kilojoule is not right answer, kilojoule per meter is also not right answer, kilojoule per kg Kelvin is not right, only the kilojoule per kg is the specific internal energy. And the value of specific heat at a constant volume for air, 1.005 kilojoule per kg Kelvin is the right answer. Remaining, this is for CV. These two are wrong. And the sign convention, both work done by the system and heat supplied to the system or respectively are work done by the system is the positive and heat supplied to the system is also positive. That's why both positive, positive and negative, negative and positive, both negative. First A is the right answer. Which of the following is a path function? Work is the path function. The remaining are not the path functions, only point functions. A bar is equal to 10 to the power of 5 pascals is the right answer. So change in enthalpy, delta H is equal to mcv T2 minus T1, which is nothing but the change in internal energy. mcp T2 minus T1 is the change in enthalpy. This is not the right answer. This is also not. Only B is the right answer in this. So some of the assignments, let us have small assignments in this. Convert 100 bar into pascals, kilopascals, megapascals, kg per centimeter square. I think it is very easy answer for us. And determine the specific volume and density of air if mass is 78 kg and which occupies a volume of 50 meter cube. Specific volume means simply volume per mass, whereas the density is mass by volume. So with this, let us conclude this lesson. Thank you for patient hearing of this lesson. If any mistakes, you please recall me, and thank you one and all.